Assalamualaikum and good day everyone. Welcome back to Dynamics course SEMM 1213. Let's talk about curvilinear motion, a subtopic in the kinematics of particle. Consider a particle moving on a curved path in a two-dimensional plane. There are two main observations for the motion parameters that describe this motion. The first observation is the velocity vector is always tangent to the path of motion, and it acts in the direction of motion of the particle. Magnitude of the velocity may differ at different locations on the path of motion. The second observation is the component of acceleration always acts in the direction inwards to the curvature. This is the reason why the path of motion becomes a curved path. Magnitude of the acceleration may also differ at different locations on the path of motion. The previous two observations can be proved by examining these figures. The fundamental understanding on how velocity and acceleration behave is crucial for analyzing curvilinear motion for particles as well as rigid bodies. In two-dimensional space, we are focusing on three analysis approaches when dealing with curvilinear motion, namely SY analysis, anti-analysis, and R-theta analysis. These approaches are based on different chosen axes. However, it is worth noting that the general relationships of displacement, velocity, and acceleration used in rectilinear motion analysis are valid even for curvilinear motion analysis, regardless of choice of analysis approach. The selection of analysis approach depends on how data is being specified in a question. For example, information on radius of curvature usually indicate anti-analysis is needed to solve the problem. Certain types of motion is suited particularly well for certain type of analysis approach. For example, problem involving projectile will normally be solved using SY analysis. Let's start with XY analysis. In this analysis approach, the particle's motion parameters, i.e. displacement, velocity, and acceleration, are decomposed along x and y axis. The origin of the x and y axis is at a location which is not coinciding with the particle location. The typical curvilinear motion problem solved using this approach is projectile problem. The projectile problems involve particles or objects flying through air with only gravitational acceleration as the source of acceleration in the system. The gravitational acceleration, normally termed as g, is taken as 9.1 meter per second squared directed downward towards center of Earth, or typically along negative y-axis. Since the gravitational acceleration g is a constant value, we can use the equations for constant acceleration previously used in rectilinear motion analysis. These equations can be applied separately for x and y-axis. The solutions between these axes are connected through time t. This figure shows a projectile moving from point A to point G. As the motion starts at point A, time is 0 there. As the projectile moves from point A to G, value of time increases. It is worth noting that the projectile can be at different points having the same height or displacement along y-axis, i.e. point C and E. However, this is possible only at different values of time. The second approach in analyzing curvilinear motion is by using the anti-analysis. In this analysis approach, the particle's motion parameters, i.e. displacement, velocity, and acceleration, are decomposed along n and t axis. The origin of n and t axis are located on the particle itself. The tangent axis t is tangent to the curve, while the normal axis n is normal to the t axis and pointing inwards of the curvature. We know velocity will always be tangent to the path of motion. Hence, velocity exists along the axis only. No velocity component will be along n axis. Generally, acceleration will have two components along t and n axis. The component of acceleration along t is optional and depends on speed or the magnitude of velocity. However, the component of acceleration along n axis will always exist for a curvilinear motion and depends on magnitude of velocity and radius of curvature. This slide shows how we obtain the equation for the component of acceleration along an axis. We assume constant velocity condition, which leads to zero magnitude for the component of acceleration along the axis. Thus, the acceleration component obtained through these equations must belong to the n-axis. Consider a particle moving in a curvilinear motion from point A to point B. The component of acceleration along n-axis, an, will always exist at any location on the curvilinear path of motion. Hence, acceleration always points inward of the curvature. However, component of acceleration along t-axis, at, depends on speed. As speed increases, at follows the direction of velocity, and if speed decreases, at acts in the opposite direction of the velocity. When the speed is constant, at becomes 0 as at is the rate of change of velocity. The last approach considered here for analyzing curvilinear motion is the r theta analysis. In this analysis approach, the particle's motion parameters, i.e. displacement, velocity, and acceleration, are decomposed along r and theta axes. The origin of the radius axis, r, and the angle axis, theta, is located at arbitrary location away from the particle of interest. The r-axis starts at the origin and passes through the particle, which is located at radius r from the origin. The theta-axis is perpendicular to the r-axis, and its assumed positive direction is normally given in the question. In the r-theta analysis, component of velocity and acceleration along r and theta-axis are obtained through following equations. A single dot represents differentiation with time once, while double dots represent differentiation with time twice. The components of velocity along r and theta axis can be derived by examining these figures. They contain only the terms having differentiation with time once, i.e. with single dot. The component of acceleration along r and theta axis can be derived by examining these figures. They contain the terms having differentiation with time once and twice, i.e. with single and double dots.